Okay, next up are Greg and Kirby. And you have a lavalier, and Kirby, I'm going to give you the handheld.
I'm Greg Scallon from Commercial Computer Systems. The project we're going to talk about today is called The Simple Executive. We want to start out by thanking Tom, of course. He was our PM. He's the one that introduced this to GNU Radio. He's the one that suggested the particular flow graph that we have that we're going to talk about. We also want to thank Ben, Jonathan, and Marcus. Marcus was very helpful getting us up and going and giving us some initial data, performance data. We'll start out by looking at the flow graph that Tom had given us. Since we were quite new to GNU Radio, we picked one that was, from a system engineering standpoint, quite simple. And we're a system engineering outfit. So we look at this and we say, aha, it's nothing but a series of 14 different blocks, and they're all run in series. What's the big deal? Well, then we found out that each one of these is an interesting block. Each block is literally trying to run continuously at all times, waiting, of course, to make sure that it has an output buffer available where it can put the product, and that there's valid input available at the input so it can run, and then it just runs. So it's all data-driven, which is kind of new to us. Most of our experience had been with event-driven, so we had to go into this interesting mode to go back and adapt our tools to incorporate this data flow type stuff. First thing we did when we looked at it is we said, that's great, and what are we going to do about it? So the first thing we're interested in as system engineers is do more with less. So what we want to do is make this thing run better, faster, smoother, improve it in some sense. Well, the mechanism that the flow graph itself starts out, and it reads a file. The file was a movie. The movie was about 10 minutes long. The movie was represented in the file in complex numbers, size about 50-some gigabytes. Then the playback then is run as fast as we can. The movie itself was about 10 minutes long, and so if the playback runs faster than 10 minutes, it's real time. If it runs slower than 10 minutes, it's not real time. Since the entire system is all data-driven, it'll process the data as fast as it can. Well, it can read the data quite rapidly. And the first thing we noticed in here, we plotted on here with the big red numbers, that's the cost to do that block. And the cost is measured, what fraction of a GPU does that object take when this thing is running at constant speed? And we'll see the big thing right away is that a lot of the blocks are small, 2%, 3%, 1% kind of numbers. The big one on here is 100% really, and that's the first block, and that's the RX filter. The RX filter takes a certain amount of time to process one sample of data through one buffer full. To generate that buffer, the read from the file or the file source block that feeds it, it runs literally 33 times faster. So it literally, the front end block is waiting until the big one, the RX filter, actually processes one block so it can give it the next one. Everything downstream of the RX filter, of course, is it's starved for data. They can process data faster than the RX filter can pass it on. So it meters all of the work that goes on. So if we want this thing to run faster, process the entire movie in fewer seconds, what we have to do is we have to knock down the size or make the RX filter run faster. So that's the first charge that we had. We talked a little bit about this on Tuesday. The mechanism we came up with is that let's go back and since we don't want to change any of the code, we're probably not qualified. We don't want to change the flow chart or the flow graph that was given to us. So then it's the mating of the software and the hardware. So this is looking at the hardware. The hardware is Intel i7 class machine. The Intel i7, the top half of this graph shows if you would, the functional schematic, the layout of the memory hierarchy associated with the Intel chip. We look at a particular core, we'll take a look at core 1, for instance. Core 1 is linked to core 2 over an L3 cache. So all the cores are linked together over an L3 cache, and the L3 cache is an interface to the RAM. Within each of the cores, in the hyperchannel type arrangement, there are 2 general processing units. Here we color them red and green just to keep them separate. And those 2 share a floating point unit. since most of all the processing in the particular blocks that we had were typically computational heavy relative to floating point, we expected that the processing in this form, that GPU A and GPU B would compete for the floating point unit and slow each other down. Turns out not to be the case. It turns out that the big thing in here is that the L2 provides cache, a communication path. The numbers here, if you're looking at a 3 gigahertz machine, the L2 cache takes about 3 1/3 nanoseconds to communicate. If you have to communicate between cores, it takes 5, 6 times as long as that. And if you have to go through RAM, of course, it's many, many times longer than that. So then we decided that if we want to make the RX filter run faster, we don't want to redesign the filter. You could, for instance, go back and parallel them, have 2 filters, even and odd, and play some games, but that would change the flow graph. You could take the RX filter, cut it in half into 2 filters and chain them together and have different machines working on them and stage them. That also would change the flow graph. But you could put the RX filter and dedicate it to one of the GPUs, and if you put the input block and the output block in the sibling GPU, in this case we showed them as red, having the file source, providing inputs to the RX filter, and we had the receiver, the floating point, the PLL, taking the output of the RX filter. If you could bolt those or lock those into a particular core, now you could exploit the L2 cache, and you'd actually improve communications. You'd cut down the cost or the time cost for communication or increase the bandwidth. We tried this and it worked fine. In fact, actually we got something like 18% improvement reduction in the time it takes to make the particular RX filter run. And we haven't changed anything. We didn't change any data design, didn't change any flow. We just went back and reallocated the hardware. Now this, of course, only works if you lock the RX filter into the same core. Many of the current operating systems go back and try and load level everything, so the next time the RX filter would run might be in some entirely different machine. Of course, what you're doing is dynamically setting up all kinds of communication links through the various caches between the cores, and that's going to cause a lot of overhead. So when you lock these in the front end, we found, like I say, an 18.3% reduction in the amount of time it took end-to-end to process the whole movie. We applied this to some of the other pieces too, but you don't really, since they're being starved anyway, the fact that they run faster just means that they idle a little longer. We looked at all of this, and then we said, well, let's go back and look at the L2 cache and the buffer size. Buffer size was a parameter that we thought we could manipulate. And we looked at this and we said, well, the natural block size coming into the front end of the RX filter seemed to be about 2.7 kilosamples, each sample being a complex number. That's 8 bytes. So now we're up around 24 kilobytes. And in order to run the RX filter as fast as we can, in other words, end-to-end, make it run continuously, you have to double buffer stuff. So that 24 kilobytes becomes 48 kilobytes. The same logic applies to the output of the RX filter, so another 48 kilobytes. And of course, the product of the receiver, the FPLL, communication onto the DC blocker in the adjacent core, it's going to need some buffers. Same numbers apply. So another 48 kilobytes. So right away, you've got 132 kilobytes worth of storage right there. Well, the L2 cache is a lot larger now, another 124 kilobytes larger than that. And through the L2 cache, it also has to run all of the code. It has to stream all of the code from RAM eventually into the processors. Not shown on this diagram, but the processors themselves actually have an L1 cache. And for the instruction part, it's 32 kilobytes. So if the code would happen to fit in 32 kilobytes, that's great. It would run through the L2 cache once and just reside in there. If it's larger than that, it would overflow into L2, and then you have a slowdown factor. Since we didn't consider ourselves authorized to go back and start changing the code, whatever it is, it is. And the net result is that the behavior, the cache improvement in this case, fits nicely. If we look at the next one, when we went back and we experimentally went back and we looked at the various buffer sizes. And bigger buffers gives you the economy of scale. In other words, amortizes the overhead. If the buffers are too long, you get this overflow from the L2 cache into L3, et cetera, and that's going to cost you a lot more overhead. So we experimented with different buffer sizes. And you'll see this chart in here. funny. The 48 kilobyte is just around the right size of the sweet spot in this entire thing. So we lucked out, so to speak. And we went back and we did the trade study to show what the other ones cost. We were kind of surprised at how expensive the 56 kilobyte allocation was. And then it dawned on us that what you're really doing is the buffers are too big to get them all in there, so you have to swap them in and out all the time. So this made sense. So we were looking at this and exploiting the L2 allocation. Improves the performance by more than 21%. And again, we've changed no code, no data, no hardware. We just allocated some stuff. In other words, we're actually going back and telling the operating system to handle things in a particular way. Then it came down that for other reasons, we had to go back and look at a different operating system. In this case, we had always played around with the original one, the version 4.4.0. So all of the numbers we've given you now were all based on that. And so we showed that when you add all this stuff together, we're looking at about 23% improvement in net improvement in performance of the system. When we went back and played around with the new operating system, or more recent operating system, 4.11.2, just in the baseline configuration, it ran 12.6% faster. And that seemed kind of odd at first. And of course, it enjoyed the same kind of improvement when you went back and played around the L2 allocation game. In this case, we got about 25% improvement. So the net improvement in the new operating system was only 11%, as opposed to double that in the old operating system. So we asked ourselves why. And the logic we came up with was, Intel's got a lot of interesting things. One of them is a thing called this turbo mode, or turbo boost. What it is that they turn around and they look at the allocation of the processors, they look at the amount of energy that's going into them, the voltage, they look at the temperatures, and then they go back and they look and they analyze it maybe every 5 milliseconds or so, and they say, how much headroom do we have? And if they're comfortable, then they go back, and when the conditions are right, they go back and they change the base clock to individual cores. And the unit that is 100 megahertz. So if you're running at a 3 gigahertz system and you have a couple of those little notches up, you have a 10% improvement in throughput. We think that's what this is showing us right here. When we did the work and showed that you could actually go back and start packing all this work in dedicated processors, we actually allocated all the other blocks also to processors. And we allocated them all so they all fit into 3 CPUs, into 3 cores. That meant that there were other cores that were idle. So every time that the Intel algorithm goes through and looks and see who's busy and who's not, all the people that aren't busy, the energy that they would have been consuming is not being consumed, and so Intel applies it to jacking up the speed on those people that are busy. So the philosophy of an operating system to go back and spread the load, equal wear, these kind of algorithms, they work against the interest that you would have if you're using an Intel system. You'd want to have 1 or 2 processors doing all the work, and the other guy's idling, and they're giving the energy and everything else, and the cooling and everything else that they would be causing could be used to increase the speed of the few that are doing the work. So that was the algorithm, the mechanism that we used to describe, to justify to ourselves what we thought was going on. A couple of little tests that we ran didn't contradict that, but we couldn't prove that that was what was really going on. But that's why we ascribed it. The other one is that, well, what's different in the operating system? It turns out that Intel provides the drivers for their, the ATPI interface, and those drivers improved. So we think that the more recent releases of the operating system include these better control of what they call the C state, or CPU state. CPU 0 and 1 is running full blast. CPUs, higher numbers depending upon the chip, 6, these kind of numbers, says you're asleep, or you're really asleep, or you're just idling, or in other words, you don't deserve a lot of energy. You're not even maintaining the status registers internally in some cases. So Intel uses all this information to decide the best way to, if you would, overclock temporarily those processors that are in need of horsepower. Another one, when we were playing this game at the beginning of the year, the best thing you could get was the Intel 6950 without going to some exotic Xeon processor or something. And that's what we got because we didn't know what we were going to need. And the characteristics are shown in the second column. Clock speed out of the box is 3, but you can overclock it up to as high as 4, I'm told, depending upon cooling. L1 in cache is, as we mentioned, 32 kilobytes for instruction cache and also 32 kilobytes for data cache, and that is for each of the hyperthreads. L2 cache, again, for every core, it's 256K. L3 cache, 25 megabytes, and that's shared across all, in this case, all 10 cores. Maximum memory you can put on the thing is 128 gigabytes, and there are 4 channels to memory. Well, Intel's competitor finally got on the ball, and early this year, they came out with this product, announced a product called, AMD announced this Ryzen 7 series to compete with the Intel i7 series. And the lowest entry in that was the 1700. We got one of those, and default clock speed's the same. The L1 cache, the instruction cache is twice as big. That's advantageous because that means there's more likely you can put a larger program and have it resident in the actual GPU without continually refreshing it from L2. Number of cores, it comes with 8. They're all hyper-threaded, so you get 16 hyper-threads out of the thing. L3 cache, it's a little smaller than it is on the Intel machine. And again, it's shared across all the cores. The maximum memory is only half as big, 64 gigabytes. Price of memory is kind of high these days. And the access to memory, the memory channels, there's only half as many. Well, right away, we see the specs in the L2 and the L1 caches look attractive. That's something we want to play with and see how good it might be. The big feature relative, AMD, new entry in the product, that their price was a lot less. When we bought at the beginning of this year, the Intel processor was $1,700. The AMD processor was $330. So a huge difference in price. Now the question is, will it work? Can you actually make the can you actually host any of this application on the AMD? And what problems do you have? Or is this all vaporware? Because this information we showed here is taken from the spec sheets, et cetera. And you're not really sure how they calibrate that stuff. And to answer that question, I want to introduce my compatriot here, Kirby Cartwright.
Good morning.
He was given the challenge of make this work or see why it doesn't. Thank you.
Hi, I'm Kirby Cartwright, and Greg was kind enough to pay me to work with GNU Radio, to work with the Linux machines, and to take care of some of these problems. I actually have that very hot AMD machine in my lab at home. It's now my personal possession, and I love it dearly. I'm going to talk a little bit about the problems we had getting our ATSC FlowGraph to actually work on the AMD machine. Let's see, being the AMD machine is bleeding edge, we did have some, and I'll talk a little bit about the problems and solutions. Okay, once again, the chips are new. They came out earlier this year. Our particular motherboard, the Gigabyte GA-AB350 Gaming, was not particularly supported by Linux. Thanks to the user community and the Ubuntu forums, I did find some patches for Ubuntu 4.11.2. That's why we changed to that, to actually get that to work, and instead of seeing a stream of IRQs not supported as the operating system tried to boot. Once again, kudos to Canonical for the quick support. I would say that the chip is not perfectly supported as of yet, but it is working. Oh, a comment about GNU Radio. So far, there is not really, really good Vox support for that particular chip. There is some overlap with the Intel chips. There's a really, really good chance for performance improvement if a Vox library is written for that. On the other hand, since Linux is an operating system by programmers for programmers, analysis tools were fantastic. I think Marcus has mentioned before about HTOP and TOP. There's also another one called LS Topo, or Topo, that displays what the core thinks the topology of the chip is. That was a great help for Greg and I to understand how the AMD chip was being perceived by the operating system and try to optimize which cores are used for which particular block in the ATSC FlowGraph. On the third hand, I would really, really like to see a cache analysis tool for runtime. If anybody knows of that, please come by the booth. We'll talk about that. Something like statistics about cache hits and misses would be really, really nice. I see Marcus is nodding his head. I think that's even more important than trying to understand threads and core usage in terms of optimizing the performance of a GNU radio application. And I wanted to make a comment on this portion right here too. In our experiences with both our Intel i7 machine and the AMD Ryzen, we found out what I'm pretty certain everybody knows here. If you've tweaked and optimized a GNU application to run on one machine, well, that's all you've done. When you move to a new machine, you'll have to start the process all over again. This might point out to some of the comments that have been made during the show where we need a runtime tool, so to speak, that can optimize performance and instead of having to depend on the programmer to tweak things. Okay, conclusions a little bit. We do have the blocks running on the AMD chip. The default performance is 4% slower on the Ryzen. I think this is really due more to the lack of up-to-date operating system support. I'm suspicious that thread allocation isn't as optimal as it could be. The L2 cache does promise more support than I think we're seeing. I did want to comment a little bit further on buffer sizes. We recompiled GRC several times, changing buffer sizes, trying to take advantage of the cache. We expected that we would find a knee that would show a perfect point of optimization. Instead, we did not. If you look at the 128K size, you'll see a reverse knee. And this is where I say we don't understand that. We're kind of curious. Changes that improved performance. Once again, as in the Intel i7 chip, using siblings for adjacent blocks in a GNU application is important. Siblings are hyper-threaded cores that work well together, that they share cache. We did attempt to tune the default buffer sizes. I don't think we got anywhere with that. We did upgrade the Linux OS version to take advantage of somewhat of better thread allocation. And I guess that's it for my portion. I had a great time doing this. I loved working with GNU Radio. It's been 5 years since I worked on it last. It's much improved. And once again, being paid to actually do this was a joy. And are there any questions for either myself or for Greg?
Thank you, Greg and Kirby. All right. Do we have? Oh, we have one over here.
What architectures are missing from Volk that are in Ryzen?
That's a good question. I'm not sure. If you want to come by the booth, we can actually go through the list of floating point instructions, the specialized ones that I compiled that show that the ones that are not supported and the ones that overlap with Intel. But there's probably at least a dozen, half dozen or so.
Okay, and we have one. All right. Right here we have Andy.
How close to real time did you guys get it to decode?
This whole flow graph was not per se meant to be a real-time flow graph. It resulted in, it took a raw, complex binary file and produced an MPEG file. I wouldn't call that real-time.
To answer your question relative to the movie was we processed 10 minutes worth of real-time movie, and we were doing it in what's it, 370, about 6 minutes.
Yes.
Yeah.
Okay,
So
and
it was better than that.
To answer your question? Okay, Andy?
Oh, Mike. Great. Hello.
Hi.
When you had this process of locking particular blocks into a GPU and a core, in that process, did that also exclude the OS from moving any other process in and out of there?
I believe it did. I can't say that for sure. But again, all of these changes were to the OS, so it would be OS peculiar capability, and I think it did.
We found a specialized kernel parameter called ISOL CPUs, where you could actually reserve cores until runtime, and then when GNU Radio would try to allocate that, so that effectively ended up, we did lock the cores away from other usages by the operating system.
But you can't lock data. You can't. And So again, if you can lock it right and the sizes are right, the data will just follow and accidentally give you what you want.
Yeah, we have Sean over here.
By the way, I'd like to comment, once again, Linux is an operating system for programmers. So of course they had a parameter for that.
Did you use any of the features within GNU Radio itself, like core affinity assignment and
Absolutely.
buffer sizing? Okay.
Buffer
Yes,
sizing
buffer.
required a compilation.
Right.
That there was a macro that defined the buffer sizes. It would be nice in the future for tweaking if that was a runtime change, but yes, we did use
Yeah.
core affinity.
Okay, so did you also do kind of a side-by-side comparison of where you went and like basically told the OS, like, I'm going to reserve this core,
Right.
rather than like GNU Radio, which is a process just like everything else, and do infinity within that process? So that's kind of to Andy's question of moving stuff in and out. But did you compare kind of like with no change versus using affinity only versus OS?
Absolutely. Basically, the thread per block scheduler, it will let the operating system handle core allocation. When you do affinity, by the way, that's
You
more or
lock
less
it.
just a suggestion as to which core will be used.
Yeah.
I'm not sure I'm answering your question.
Yeah, thank you.
We have one more over here.
Hi, yeah. So you briefly mentioned that you saw that the cores could actually scale their frequency in an attempt to kind of preserve
Right, that's
efficiency.
the turbo boost.
Right. When you guys actually ran the test, did you lock the frequency to a fixed setting?
Oh,
or did you
Not wanting to play hardware engineers, we decided that we would run everything with whatever the default settings were from the manufacturer. That's why we ran at 3 gigahertz. We didn't try and overclock anything. We didn't try and explicitly match the memory speed or anything. We just said, hey, it runs right out of the box. We're going to use it that way. We did not try and block anything nasty. Am I answering your question? Kind of?
Yeah, a little.
You want to try it again?
Okay.
Okay.
If I may, I'll throw out a comment.
So there's a governor, the CPU speed governor, that can
Right.
automatically scale the frequency up and down.
Right.
And from the kernel, you can explicitly tell it what
You
mode
can
want.
explicitly disable it. I do not believe that you can go back and tell it that, hey, I want to direct all of this energy only to core 1 if you have any spare energy. I don't believe you can do that. The AMD promises that they'll monitor stuff at a lot higher rate every millisecond, and the increment that they have is only 25 gigahertz. So they have many more steps, smaller steps, so they can better match stuff. And the literature implies that you can go back and direct it to a specific machine or specific core. But again, we've not done that.
I'll answer from my perspective, if I may. We found out that there is a way to control the states of the different cores, but this came a little bit late in the game. It's on my infinite list of things I'd like to try.
All right, any other questions? Oh, we have one down there. I think I might be the closest trip.
So just to talk a little bit more about the governor, there is a performance governor, which is not the default, that when you use it with the Intel chips, it prevents them from stepping down in frequency and keeping the highest frequency that they can run at. So that would be something else to look at. It's simple to do.
Okay, thank you very much. Both Greg and I come from a hard real-time background, so this idea that a CPU will actually change performance from moment to moment,
Scary.
beyond
Yeah.
scary. So yeah, learning ways we can tell the kernel to lock in performance features, this is good to us.
One of the parameters that they monitor is temperature, and it would really depend upon when you sample temperature, at what point, and what else is going on in the box, what else is going on in the other cores. It's, like I say, kind of scary.
Yeah, we would worry about it, for instance, an avionics system that had a hard real-time constraints, and it warms up, and all of a sudden it stops working.
Yeah. Or works differently. That'd be a thrill. Yeah.
All right, thank you very much, Greg and Kirby.
Okay.
Thank you.
Just one last thought. We suggest very much that the same kind of techniques might be applied to different flow graphs, of course, using the same kind of things, and you should expect potentially an improvement. Thank you all.
Thank you, Greg. So I do want to point out that they are Simple Executive is a diamond sponsor of the conference, and they have a booth in the tent. If you haven't talked to them yet with your questions about optimizing flow graphs, please do today.